now that we've had a chance to kind of look at some of the stuff in continuity, we briefly touched on this idea of discontinuity. And that's often what we're going to be discussing is what kind of problems the continuity has. So the first one is a removable discontinuity, and that is essentially when you have a single point missing. And as I mentioned, these are the cases that we were using limits, and we could do some algebraic tricks to fill that hole and figure out what the value was. Non-removable discontinuities, we also have some terms for them. When it looks like this, we call it a jump discontinuity. Okay. And this is when the left side limit does not equal the right side limit. We also have an infinite discontinuity. And we can also have an oscillating discontinuity. So these discontinuities here are all ones when the limit does not exist. So the same problems that when we talked about limits when they do and do not exist, they happen as well for continuity, and that's, some of that we talked about. So let's take a look at a graph and we'll discuss the continuity together. So what do you think? Can anybody find something discontinuous and classify it for me? Yeah. There's a jump where? Yep. The left side does not equal the right side. That's right. What else is discontinuous here? Yeah. Yep. Good. Any other problems? Problems? Discontinuous anywhere else? Have I made you nervous? Yeah, there's no other problems there, right? You can move your finger along any spot except here and here. Everywhere else, you can do that without picking your finger up, so you're okay. If you're not sure, I'll only give you a simple definition if it still works. So even if you're concerned like, well, I can't pick my I don't have to pick my finger up, but I'm not sure if I'm right. Well, I wouldn't have told you that works unless it worked all the time. So trace your finger along the graph there. There's no other spots. Okay, so this is where we also want to be able to discuss it, is in the world of algebra, where we don't have a graph in front of us and we need to figure it out. So I'm going to discuss the continuity with you in the first one, just so you see how it works. What is this first graph here? Do you recognize this first piece?
It's a straight line.
Yeah, it's just don't want to use a red highlighter there. Nope. One more time. Yellow highlighter there. That is just a straight line. Any problems with a straight line? Nope. It is continuous everywhere. Remember, you could just simply state it's a polynomial, it's continuous everywhere. But that's not, we won't. What about the next piece? X squared. What's that? It's just a quadratic, right? It's a parabola. So any problems with parabolas? All right, so is this graph continuous everywhere? Well, where's the only place that something could go wrong? Yeah, when we put them together. Basically, like you said, I don't want a black highlighter. Like we said, there's a line and there's a parabola. It might look like that. It might look like that. We don't know. So how do you think we can figure it out? Yeah, we're just going to substitute to figure it out. If I want to know what's the limit from the left-hand side, that's going to be -2 times 1 plus 3. So it's 1. If I want to know what's the limit from the right-hand side, it's going to be 1 squared, which is 1. So yes, these two pieces do meet. They are connected. there's no hole in this graph or jump. So yes, your initial assumption was not a bad one. It just we needed to verify it first. So continuous on the left side, continuous on the right side, and the only place that could have a problem, they are connected. So therefore, the limit as x goes to 1 of f of x is the same thing as f of 1, and it's continuous. Okay, so you take a look at the next one. Is this next graph continuous? So what do we think? Okay, so again, all I'm going to do is I'm going to check the limits on both sides. So 2 is where I'm concerned because the graph on the left side is continuous, the graph on the right side is continuous. Let's just make sure that they do or do not meet. Sorry, that should be a negative 2 times 2. So negative 4. And then the limit as I approach from the right-hand side of the function will be 2 squared minus 4 times 2 plus 1. So 4 minus 8 is negative 4, so negative 3. So they do not meet. They are negative 4, negative 3. It's not continuous. What kind of discontinuity would it be then? Yeah, it's going to be a jump discontinuity here because you jump the left side, you're at negative 4, and then you jump up to negative 3. All right, so the last one to take a look at then is this 3-piecer. So see what you can come up with there. All right, so these pieces that we're going to look at, they seem to be okay. They're defined everywhere. This one here, is there a problem with this piece? That one there, 1 over x? Yeah, it can't be 0, and we're not concerned about it because we're forcing it to be bigger than 3. So don't worry about the fact that there's a problem. It's not a problem where we're using the graph. So all we have to do is in the same situation is try and see if the pieces connect. So we'll take a look at negative 3 and at positive 3. So the limit as x goes to negative 3 from the left will be negative 3 plus 3, which is 0. The limit as x goes to negative 3 from the right is going to be 3 minus root 9 minus 9, which is 3. So that one should be a jump. Does that, anybody else get that? Okay, you're also quiet all of a sudden. Limit as x goes to positive 3 this time. And I'll go from the left-hand side. That'll be 3 minus root 9 minus 9, so that's 3. And the limit as x goes to 3 from the right-hand side of 1 over, of f of x is just 1 over 3. So there again, another jump discontinuity there. All right. So this theorem here, this is like thank you Captain Obvious for this theorem, but it is one that you'll make good use of quite a bit. There are things we can do, and you'll see later on, maybe in like a month or two, you'll go, oh, you got to use the intermediate value theorem to do this. But basically what it says is if f is, if f is a continuous function, on the interval a, b, and m is the largest value, and one more time, and little m is the smallest value, then the function f must pass through every value from or between those two. So basically it's just saying because your finger can't come up off the page, it has to trace the whole graph. No matter what the values are, it has to go between. So for example, let's just say this was 1, and let's say that this was like 50. If all I told you about this graph is that the graph was continuous, the smallest value was 1, and the biggest value was 50, you could say by the intermediate value theorem, this graph must also go through 30. It must also go through 40. It must also go through 10, 20, 15, 19, 16.739217, 7654, 8. Any number in the middle there has to be a value in the function. Okay? Because it's continuous, we know all of them are present. So this one here, without graphing, show that the function has at least one 0 in a given interval. So here's one way you can use the intermediate value theorem. If I was to substitute in, and I take a look, what's f of negative 2? So I have f of negative 2 is 12, and I also get f of negative 1 is negative 4. So what do you think? How could you explain to somebody that there must be a 0 in here? Intermediate value theorem. So and I'll throw that one at you. Do you remember what that means? Reverse E. Do you remember what it means? It means there exists. There is a C, and it's an element of, so somewhere in the middle of negative 2 and negative 1 with f of c equals 0. You can, of course, write it in English. I'll write the next one in English. That's still English. It's just math English, I guess. Yes?
The interval they give you is the y coordinate.
The interval here, these are the x values. So those x values are it's like the domain of the function. So somewhere in that domain that you want to know, I guess if you're going to go to the trouble of factoring this thing or looking for an answer, that you probably want to make sure there at least is an answer before you go looking for one. So in this other one here, if f of 0, that's an easy one. I don't need a calculator there. That's just negative 1. And so is f of 1. That'll be 1 plus 2 minus 1, so it should be 2. Okay, so by the intermediate value theorem, there is at least one place where f of x equals 0. So how do we verify? What's the only condition that the intermediate value theorem needs to apply?
It's continuous.
Continuous. So how do you verify that this is continuous? One word will do it. It's continuous because it's continuous, unfortunately, is not enough of a reason. It's a polynomial. That's one we're looking for. So now that we know it's a polynomial and polynomials are continuous everywhere, intermediate value theorem applies. We can verify that it does in fact have a 0. So f of 0 would be 8, and f of 3 would be 9 minus 18 plus 8, which is negative 1. So yes, somewhere in the middle there is a 0. And of course, you guys are probably like, this is crazy. Why are you looking at calculus? Because all we have to do is go back to grade 11 and do that, right? Factor it, and I get x equals 2 and x equals 4. Which one is the one guaranteed by the mean value theorem? Yeah, this is the one that the mean value theorem guaranteed us would exist. One place somewhere in there that it does equal 0. So x equals 2 is the one. All right. So the last thing in continuity that I'd like us to be able to do is to make a function continuous. And we've already done this. We just haven't done it with, I asked you when we looked at a graph how to plug the hole up, right? So, for example, this function, no problems here. It's continuous everywhere. It's defined. The only problem is at x equals 0. And remember, we're not letting it touch x equals 0. Question, yeah?
Does 4 sine x over x just equal 4?
You are jumping ahead to the limits, and yes, we will use that fact that sine x over x is a limit we've dealt with. Yeah, it's coming up. And then the other side of the graph is also continuous. It's just a line graph. Okay, and now you might be thinking like, whoa, why is there an a? Well, that's your job, is to figure out what's the value of a that's going to make this thing continuous. So in order to be continuous, we have to have a limit that's the same on the left side and the right side. David, there you go. Jump out there. What is it?
4.
Yeah, so this one here, that special limit was 1, so the whole thing would be 4. So the limit as I approach 0 from the left side is 4. What does that tell you about needing to make this continuous?
The right side 4.
The right side must also have a limit of 4. So the limit as x goes to 0 from the right side of f of x must equal 4. Okay. The limit as x goes to 0 from the right side is a minus 2x. That has to equal 4. Remember, a is a number we don't know yet. We have to solve an equation where x becomes 0. So a minus 2 times 0 must be equal to 4. So a must equal 4 in this case. So this graph here should actually become 4 minus 2x, and then the two pieces will meet. The left side is the same as the right, and it will be continuous. Okay, so I will let you continue on with your exercises.